So one more on acids and bases, and especially expressly on pKa. I want to finish after you've heard about those trends, polarizability, bond polarity, based on where it is on the periodic table, left to right or up or down, inductive effects or positive inductive effects, resonance stabilization, all those ideas. Once you've heard those, and you should go back and watch the first pKa video of these two, because it's really important that you understand it, not just memorized so that you understand the values, but take the time to watch some videos in the video library and make sure that you have a theoretical as well as memorized understanding of what pKa is, because it really is going to come up time and time and time again. So I wanted to mention, before I got to my 12 memorized ones, I wanted to mention one thing that I think is worth mentioning. I often don't get the chance to talk about biochemistry, but really, organic chemistry is only relevant if it's biological at the end of the proverbial day. And in this case, we have a great example of how pKa's and physiology really intersect. So let's talk about an amino acid. So everyone thinks of an amino acid as a carboxylic acid and an amine. And I'm here to tell you that that's not an amino acid. Isn't that terrible? Crisis, right? And the reason that is that the pKa of this carboxylic acid is between, depending on circumstances, 9 and 10, while the pKa of this the pKa of the amine is between 9 and 10, and the carboxylic acid is, 2-ish. So, what that means is that this amine exists as amine, as NH2, only when you get up to a pretty basic, all things considered, condition. And it means that in a very small amount of acidic or conditions that are considered acidic, this carboxylic acid quite quickly deprotonates. So what do I mean? So what I mean is at pH of 1, both of these are protonated. At pH about 7, the carboxylic acid deprotonates. But to a large extent, the amine is still protonated. And that, by the way, is what we would call, within an order of magnitude of so body pH, depending on the vesicle you're in, that's about what the pH is, or the state of an amino acid is in your body. And by the way, we have a really cool term I want you to know. It will come up in many circumstances. This thing has both a negative charge on it, a positive charge on it, and that makes it named after the guy, you can imagine, a Zwitter ion. So Zwitter ions have both positive and negative charge. If you get up to pH, let's say 11, now everything's deprotonated. So this molecule that we think of as an amino acid isn't really relevant. Isn't that remarkable? And that the deprotonated acid and the protonated amine are actually what exists at physiologic pH. Pretty powerful stuff. So I'm afraid that it's not enough to understand in a fuzzy sort of way, in a qualitative sort of way, what pKa's are. Unless you memorized about 12 of them, and it'll be okay. Don't panic yet. Um, unless you have, then you won't be able to discuss why a reaction occurs the way it does. There are trends, and understanding these trends is what makes you a good chemist. So, approximately 12 pKa values. And am I saying that I'll just ask you what's the pKa of this molecule? I'm saying that. I'm saying that I'm going to make you memorize these. But if you understand the big ideas, the trends, these 12 won't be so bad. So let's dig right in. So alkanes, methane, ethane, sp3CHs, they don't break. They just don't. And that makes us able to do chemistry on all the rest of the molecule, the interesting bits, if you will, because the long alkyl chain doesn't do anything. And it's even true that if you have an sp2ch, you have that hydrogen, it's not going to break either. So you're in a good place so far. These are really, really weak acids. And by the way, their conjugate, the deprotonated form, is an incredibly strong base. What does that mean? Think about it. If it hates losing a proton, it wants that proton back. So something that doesn't want to get rid of that proton is on the prowl for a proton to get back. So weak acids, strong bases. What's another famous strong base weak acid? I mean, something like 38. And will I ask you these values? I'm going to ask you. Now, I'm going to ask you about a weird one you didn't see coming. You might have seen these three so far, predicted them. And that's about 35. And that's not totally unexpected. You can imagine hydrogen doesn't want to break. It's a very nonpolar bond. And the reason I want you to know that is that I would like you to know the effect of that. And that is that the conjugate base, the hydride, is incredibly basic and is used in organic chemistry a lot to extract protons from other things. Think of it as something else has a pKa of 20, and this has a pKa, it's the conjugate base of something with a pKa of 35. It's going to steal that proton from that pKa of 20 because that doesn't hold it as strongly. It's more acidic. So hydrides are really powerful and useful. The next one we'll go back to is in red, sp CHs. So in this case, alkynes. We said much more reactive, shorter bonds, more electronegative. They lose the proton much more easily. In fact, I would like you to know that these have a pKa of 25. In fact, that'll play a role in some important chemistry, some important reactions in 253. So what else on our chart? Let's do a different color. We discussed this. So we call these protons alpha. And the reason that those protons can be extracted, that their pKa is lower, is because they have a resonance form. They can form where the double bond comes to the carbon-carbon and you leave the negatively charged oxygen. There's resonance stabilization, and it's big, and it affects the chemistry pretty significantly. So much so that the pKa is about 20. And you should know about the alpha protons to a carbonyl and how acidic they are. Now, the next ones are the oxygen ones, and whether we're talking about an alcohol or water, I tend to think that if you know that all of them are within a margin of error, about 16, that's really powerful. So those are 1, 2, 3, 4, 5, 6, 7. Only 5 more to go. So this is probably a bit surprising. So if you have an amine or ammonia that's protonated, sorry, ammonium, it's got a value, remember that amino acid talk, of about 10 before it deprotonates. Still pretty weak as an acid. We still consider these weak acids. That amine likes being ammonium or an amine positively charged amine. We've seen this numerous times in the 2 videos. Carboxylic acid, resonance stabilized. That's why it can lose that proton much more easily. Generally speaking, around a value of 5. We're now at a point, well, we've seen this in the prior video, that HF is about 3.2. We know that's because it's small, it's not polarizable, it hates having a negative charge. When you think of these, often you think in terms of how well can they break, and you should be thinking, well, how well can they survive on their own? Solid couples, right? And in this case, F minus is a terrible anion because it's hard and dense and it hates having that negative charge. It can't spread it anywhere. So all of these could be called weak acids. In fact, somewhere around 2, it goes from weak to everything in the next column strong. So the first one I want you to know is, remember we did ammonia or amine, 38, and then the protonated ammonium or the protonated amine, and that's 10. So we've done oxygen in the form of water or alcohol. What about protonated water or protonated alcohol? Well, this is a much more polar bond. The oxygen, the hydrogen, the proton sits on those 2 lone pairs in that tetrahedron. Much more easy to lose. In fact, 10 to the 2. What does a minus number mean? It means that the deprotonated form is more common than the protonated form. It splits apart very quickly, very easily. It tends to be split apart. And then I would like you to know the rest of the halides: HCl, HBr, HI. I like -8, -9, -10. Oops. So what do I have? 1, 2, 3, 4, 11, 12. I've got 12. So am I going to ask you what the pKa of protonated water, otherwise known as hydronium ion, Yeah, I could do that. I'm that kind of person. Could I ask you what the pKa is of propanol or butanol? Yeah, I will do that. You'll know that it's around 16. Um, will I ask about carboxylic acids, protonated amines, any of these? I'm going to ask. I'm going to ask. Because you should just own them. Your life as an organic chemist and as a biochemist are just going to get so much easier if you know this, if you don't have to constantly be looking in pKa tables. Now, do I know myself the pKas of a lot of the species outside of this? I don't know, but I can look it up, right? And there's always these, what is the pKa of a chlorine on the protonated alcohol, and how does that inductive effect lower it even further? There are details. But if you know these 12, you're in a good place. So thus ends chapter 6, and thus ends sort of us learning the rules of chess. We've had a lot more theory than you can imagine in, what is it, 4 weeks, 3 weeks. We've had a huge amount of theory. We've developed all these tools for talking about strain, and we've talked about torsional effects and sterics, and we've talked about protic and aprotic solvents. Now we own acidity, pKa, reactivity. We own a host of things. Now in chapter 7, finally, we get to do some chemistry. So below this is the next video on the chemistry of organic chemistry. We'll finally do some reactions. And I hope you find it stimulating. I hope you find it fascinating. And I know you'll find it challenging because there's a lot to talk about. But if you understand, if you take some time to think about inductive effects, the polarizability of molecules as they grow, I should have included sulfur in this list of 12. I should have made it 13. We'll do it as we get there. If you understand bond polarity, all those things, we can do some organic chemistry together. So I look forward to seeing you in the next video. Thanks for your time, and well, have a good day.